The talk of this is really a consequence of, in every Who Am I session, I always say, well, I don't really believe in formalization. I think we should do something else, which I call flexiformalization. And I like to start my talk in coming out against what everybody else holds dear to their heart, in this case formalization. But I've been kind of polite, and the lower line kind of says what I really want to talk about. So I would like to, so when I was preparing for this talk, I was kind of I had a hard time starting off with this talk. But what finally brought me some clarity is this question, which has not been asked, I think, enough in this trimester, is why are we formalizing after all? The overt reason of the mathematicians seem to like it, I think, is not an answer. I have 7 other answers that I've kind of partially heard along the time. Here's one. It's kind of what I call the reliability answers. It's in a short form, if mathematicians are unreliable and the reviewing is broken. And we can help because we can have a theorem prover that is reliable and shortens reviewing, at least for some aspects. That's quite condescending, I must say. We shouldn't really use this too much. It's also wrong, I think, all the relevant math. So math papers really fall into 2 categories. One half is nobody reads them. It's perfectly fine if those are wrong. And the relevant ones that are read widely, those are being eyeballed enough. There are some things that are so prominent or scary that this may be untrue. But that's not for us to decide, I would say. And yeah, if you think of it in a computer science information theoretic point of view, we're gaining very little by just the reliability. Everybody believes, like, depending on how much the trust on the informal refereeing process is, this has something like 1,000th of a bit of information because we thought it was correct anyway, right? These kind of things. That's not an answer I like very much, but we're giving it quite a lot. The second one that I've observed a lot, formalizing in lean, Koch, Isabel, all of this, is a lot of fun. And we're going to do it anyway, because we're all mathematicians at heart. And it's even a challenge that is like other challenges. It's like climbing Mount Everest or Mont Blanc, where you have a very tedious but very satisfying and tiring process, and at the end there's this second where you reach the hill and then you formalize Mont Blanc, and in the mountains you have to get down without dying. But that's even better here. So I think this is a very well accepted answer, I think. We're getting proofs. And proofs are really why mathematicians are doing this whole game of rigorous math. They give us much more than just reliability. So maybe we are doing formalization because it gives us proof. But empirically, nobody really looks at them again, and we even have proof irrelevance, which I think is a slap in the face of mathematics. So whether we believe in this answer as a community, I'm not quite sure. Automation is probably a good answer. We can do more math that way, possibly. I can see this in terms of program verification, where we need to do much more math for computer science. I can see this for, say, applied math, because somebody except myself cares about this theorem. For pure math, where only the pure mathematicians understand and care about the theorem, this is questionable, right? There's always been the self-defense of math, well, but if we're letting mathematicians do what they like to do and don't care about whether these things are applicable, then we're creating lots of little mathematicians who can then go into finance and revolutionize AI or do all of those kind of things. That's the probable societal cause why we're funding math anyway. And it's unclear whether automation in pure math I don't know, right? If we're automating math and maybe even automating the conjecturing, we can run the whole math game inside a computer, inside a server without a terminal, and nothing is going to change, even though there's gazillions of new theorems, right? Yes?
I don't want to derail you too much, but you know, like today at 5 p.m., my OEIS looper just proved 126, or I discovered 126,000 explanation. So I have 126K discovered OEIS programs now. And like this is going to be so big, the fact that we automate not just math and science, but we also verify thanks to all this stuff that we are building. And this is going to be such a crazy feedback loop that will automate science. But like I really very strongly disagree with you when you are saying that math is in some particular, like Shankar and Mario were saying that 30 years from now we will be living inside theorem proofs. It's so much true. Like the AI people have no other clue than to basically verify like all these AI systems that are being done.
It seems I'm reaching my goal. I'm provoking another one.
You've certainly been provoked.
Not all of these answers I subscribe to, but that is an answer you could have. And by the way, we did the same. We had, I think, 3 million new identities in OAIS, and the only thing we could really use that for is a distributed denial of service attack on the reviewing on the reviewing system of OAIS, which they didn't, which they actually didn't thank us for. When we tried. We gave them 3, and they accepted 2, and 1 directly had a human corollary, and another they rejected as too easy. And when we asked them, would you like the other 3 million? They said, no! Right? Okay, I'm ambivalent about this. One answer I subscribe to is big math. We can actually, and in the process, and we're seeing this with these nice green and red and blue and so on bubbles, we can organize teams around things because the bookkeeping of the whole thing becomes much better and much colorfuler, clicky-er, and so on, and we can organize bigger teams about, which means we can probably do things like redo things like Fermat's theorem, or the classification of finite simple groups, which has been foundering for 15 years because the bookkeeping couldn't be done, right? I think of this as the one-brain barrier, and maybe together with the systems we can actually lift that a little bit. We're using it, we could say, for proof education, because using theorem proofs and formalization is a game. That's like climbing Mont Blanc, which not everybody can do, but everybody can take Lean or Isabelle or ETPS or whatever. We've seen the examples and kind of learn proving that way, or at least learn our view at proving that way. The math view of proving is slightly different. And there's a nice social side effect. You're not actually, the students are no longer fighting the nasty professor who always says, no, you can't do that. But the professor and the student together are trying to convince the nasty theorem prover who said, no, you can't do that. Right, so that's a nice thing. We're only doing this at a very, very, very small scale so far. I'm trying to kind of refute all the answers a little bit. Right, one of my favorite examples is math education, where it's not about educating people how to do proofs, but what are the contents, Right? What is a constraint satisfaction problem? It is a 7-tuple blah-de-blah-de-blah-de-blah-de-blah, and how do you deal with it? And what we're doing is we're basing this on formalized statements, not proofs. Examples, positive and negative ones, problems, misconceptions, and all of those things kind of conspire that we can automate the didactics. And the fun fact is most people who are teaching math are not teaching to mathematicians, but to physicists, economists, social scientists, and all of those kind of people. And this is maybe the main influence of math and the other reason why they're still keeping us mathematicians around in universities. And if we could do something there, then maybe get better, that would be a nice thing. You can't do it without formalization. You can clone mathematicians. That's how we currently do it in the AI age. Maybe we should do something else. So these are 7 answers. Think about which ones you subscribe to. It's important, I think, to think about this because they kind of inform us about what we're doing and help us answer whether we are succeeding, which I think is scientifically very important to know. I basically subscribe to the proofs, big math, and STEM education, and of course fun. Your answer might be different. Yes?
Are we allowed to say all of the above?
Yes, you are allowed to say all of the above, but then do what the behaviorist does. Have you ever actually looked at a proof other than trying to get it unstuck? And if you don't, maybe you shouldn't answer 3. Yes?
I have 2 ones that might not be in your list. One is aesthetics. I think a proof object in ladder calculus is a very beautiful thing, like a diamond or something like this.
Yes. I subscribe to
like
that.
purity or something, so it's a bit in the fun order.
Yeah.
And the other one is documentation. So some genius mathematician says the ABC conjecture, it's obvious that, and then it's obvious for that person, but maybe not for me.
Yes.
In the proof assistance, I can do the Leslie Lambert thing and click things open and really find out what is going on there.
Yeah.
So it's like the completeness of the thing. That in 1 century, when no one knows the subject anymore, it's still there.
Yes.
And I don't know which of your answers has that dimension.
Yeah, some of them are non-disjoint, I would say, but I think I should add them. But then, of course, I need bigger slides. Yes?
And I think often before you're formalizing, it's not entirely clear what the informal text actually means. And so this is very much the extent of your second answer. Now it's clear what it means. Everybody now has the same model of what that statement actually means.
Can I have another answer?
Yes.
Why not? I mean, in the sense that, suppose I'm stuck on a proof, then I can take a run, do the dishes and think about the proof, get further. But you can also formalize it as a way to spend your time while thinking of the proof. And then you don't need to think about, is this lemma really true? Do I need to check it again? You can just move on.
Yes. I love formalization if, like in climbing Mont Blanc, you actually count the whole ascent while you still have aching knees and pumping lungs and all of the things you can see in between and so on. If we count that more than just the fact of having a formalization. And I'm not sure that we're always in our communication differentiating that enough, which is why I bring up Mont Blanc. So my problem with formalization as a process that goes from a vague idea or an old paper or those kind of things is that our systems just support us essentially in the last moment. Right? We can not write all the nonsense that we're writing or possible utter nonsense we're writing down in between? And for me, the answer is flexiformalization, as you probably have guessed. And I want to take the rest of the time I have to kind of say a couple of those things and see how far we get. Any other objections to this list? Yes?
I also have a mountaineering allegory. So I was at some point a bit annoyed that people take it for granted that flexibility is a good thing. Mm-hmm. And if you are climbing a mountain, then it's good if your rope is flexible, but your ice axe should not be flexible. So some things should be flexible and some others.
That is a very nice. Thank you. That I have to remember. Righto.
I think there is something that is very important, that is certification of industrial products.
Yeah. The only thing I want here, and this is just an attempt to provoke you and get you through the next coffee break or lunch. This is not really what I'm what I want to talk about to you as at a technical level, but I'm perfectly happy of turning this into a work group. Right. So I'll kind of keep adding to that. Maybe there's a list not of 1,000 theorems, but of 10 plus answers to why are we formalizing.
It's called a QED manifesto, and it has been written 30 years ago.
Well, now it needs to be rewritten. But they have some of these things they haven't had in there, possibly because they were still thinking about automated theorem provers mostly. Yes.
I was going to say that, I think I'll take all of the above, but, kind of rewriting what's after, right? Because it's reliability, yes, but it's not because mathematicians are unreliable and reviewing is broken. Reviewing is broken, but, it's because I am unreliable. I know that I need some help with very boring stuff when it comes to cut elimination proofs, for instance. So all the other ones I have a slightly different way of looking at them, but it's all of the above.
Probably because you're more polite than me. I'm not sure I would give the mathematicians these reasons. Yeah. Okay, so I want to say a couple of things about flexiformality, which I think we're kind of doing as a community, but we're not actually feeling comfortable with it. And I think if there's something I can do here that gets you to embrace more of what I call flexiformality, then that might be a good thing. So you might, and that's something that I see here every day, we see that math is mostly informal. I think we have 120,000 papers per year in pure math, and they all have kind of 3 or 4 or 5 or 6 or 7 theorems in them, but we're not seeing 1 million research level theorems a year formalized. Oops, why is this not? Okay. Sometimes it does. Right, so we would love if we map the number of math against their formality. We kind of have this steep cliff on the left, and most people here with math would really like to move it to the red curve where everything is formal. Maybe not the emails, but everything that is relevant math is actually formal. And that's actually a big jump, as many of you know. Wouldn't it be much nicer if we kind of had the situation where kind of only the documents that count, like the journal publications, are formal, and then we have a big mid-ground that are somewhat less formal, but maybe so that we can do things with it, and then some of the high-ticket things are actually fully formal. Which would, if we had something that kind of is like the way up to Mont Blanc all the way, then we could kind of do things in little steps as we are doing mountaineering. We take one step after the other, and every one of them hurts, but every time we go a step, we see more other mountains, all of those kind of things. It'd be nice if we could then maybe kind of farm out things, formalization steps to different experts. Right? Those kind of things. That would be very nice. What we need for that is not something like Lean or Cog or so, which has a formal logic in which you cannot write down nonsense. But we need to have support for what I call the possibly utter nonsense fragment of math. I think it's so important I'm going to write it down. Possibly utter nonsense. There we go. Okay? So that's something, why? Because then we can support and control the whole process, and driven by need, the systems actually do steps in that direction. Blueprints are just one of them, and it looks very nice and it has nice colors. Wouldn't it be nice if we had a continuous process? Also, I believe there are more things than just saying, yes, we have a proven theorem. We have had a work group on search. And for all of that, we have to do change management. That has been talked about a lot. Proof search, proof checking, and so on. And it's interesting to kind of map basically the functionality you get against the formality you need. If we accept that there's something like flexible formality, then proof checking needs a fully formal proof. Everything has to be completely formal, and then it can say yes or no. Right? It kind of can do nothing in between, essentially. Yes, you can cut it down into little lemmas and so on, but that doesn't really matter. Then I apply the whole thing to the lemmata. Interestingly, proof search has a better profile. Why? Because it just can say, oh, put your proof here. You need less formality. You can leave the proof unspecified. Just have a meta variable for it, if you will. Yeah.
Do you have any idea how to turn this diagram into something that's not like just a drawing and like actually measure these quantities?
Yes, you need informal math lib for that. And if I ever get to my conclusion slide, unlikely, then that's something.
Well,
that's really what this talk is about.
No, I mean more specifically, like how do you quantify formality and functionality? What puts you up on the functionality other than like, oh yes, I get things done? Like,
you could say math productivity is something you could micro-measure math productivity, which is how quick are you in reading a proof and those kind of things. And I think it's an excellent question, and I would love to make progress on this, but I haven't yet. And I think as a community, this would be just having numbers to this would be right. I do believe that the things are somewhere in those ranges. And they're much more bumpy, I'm sure.
So an obviously flexiformal world is computer algebra. I mean, that's very flexiformal, right?
Yeah.
I mean, it looks formal, but it's nonsense if you are into semantics. So
possibly utter nonsense, you might.
Yeah, I agree.
So if you want a corpus where you have metrics like Mario is asking for, you might study that world as well.
Yes, and we do. And we study OEIS, which is right? Their formulae are just, they don't even have dollars around it. We parsed them. That it's
Well, when you, for example, in OEIS, you can go to proofs and you can,
of course,
show
and we
that
did.
some
We've done it.
explanations are wrong but interesting. Well, like
Absolutely.
pseudo primes, right?
Yes,
And
absolutely.
then your levels of quote unquote, I know flexiformality is probably the right word, but like it's still a semantic object. It just does something else than you thought, right? Like
Absolutely, and you don't have, you're preaching to the choir for me, right? We've been doing OEIS for 10 years, and we're doing these things, and we find them interesting, and I think they're very, very important. They're like the climb all the way, and full formalization is at the top. Right. So you, Mario, have asked, how do you quantify how do you quantify more formal than, essentially? The lower thing. The other one is also interesting, but I haven't thought about this so much. I have a qualitative philosophical answer to this. So linguistic posits that the meaning of language is something in our brains, yes, but we can model it by transforming things into logical formulae. That's what linguistics was before LLMs and machine learning took off, when it becomes completely unclear what that is. Mathematics of natural language. And so if you actually think about every natural language sentence or text or whatever, I don't care, has a meaning as a logical formula, then it's very natural to say, well, but there might be multiple logics I could formalize into. So linguistics says the meaning of informal math is formal math. Wonderful. Say we could do this. Say we had a relation that says this is the formalization of that. Then we can also define more formal then. So you have something like, I imagine the space is, we have the space of logics here, and we have the space of expressions that gives a nice Cartesian product, which of course is not actually two-dimensional. We all know that. I'm going to draw it like that anyway. And then kind of you have a portion of all formalizations that is math. You have maybe V models in software engineering, and you have somewhere down there love poems and all of those kind of things. I'm only interested really in the math, and kind of, you can probably say that there are variations and so on, so there's a kind of an area of formalizations for any given informal math, and then you basically can say A is more formal to B when the set of its formalizations is smaller than that of B. Seems like a reasonable thing. It's not measurable, sorry, right? Or it's only measurable if we have many more formalizers than we currently have. But at least this gives us a starting point. And the process of disambiguation, what we do, right? Whenever you see the word group in an informal text, it could be the algebraic structure of a group. It could be just a run-of-the-mill group of things. It could be a LaTeX group with the curly braces, and all of those kind of things. You need to disambiguate, and that typically kind of either makes disjoints sets of formalizations or contained sets of formalizations and so on. And you're getting nearer and nearer and more formal and more formal. And that's the process I want to understand. I'm not sure this helps you. It really helps me. And then you can, I really like this. This is, by the way, a picture of flexiformal, right? Formal as in dressed, and flexi. Stephen Watt came up with this in the pre-generative model, so this is already, I think, 10 or 15 years old.
It's not an AI picture.
Huh?
All the AI pictures.
It is not an AI picture. It is not.
This happens all the time.
Yes, but he could do it before that, so it's an NI picture. Okay, right. Okay. Yes? Any questions here? So I do believe formalization is something we can get a handle on. We're doing it practically, but this is kind of the theory part as far as I got. If anybody had better ideas, tell me. One of the things we've learned while practically formalizing is that theory graphs, as they've been bandied about here, Jacques does a lot of that, Florian does a lot of that, we do a lot of practical things with that, are very important. Here is one. So the main idea is, rather than having a huge ontology of math or any other subject where everything has to be true at the same time, we allow ourselves swarms of little ontologies that inherit from each other, that are informed by each other, and so on. And they can even be mutually inconsistent. They might still be true. Physicists do it all the time. Some of them believe that proton decay is in 10 to the 14 years, and some of them believe it's in 10 to the 16 years, and nobody knows whether it's correct, but you have kind of two versions of physics that build on these things, and maybe in CS some people even believe that P is equal to NP, and you could do math based on that assumption. So what do we have? We have basically inheritance in these theorem graphs. We have named inheritance, which makes it very nice to say, well, a ring is actually a monoid and an abelian group, but one for plus and one for times, and do the inheritance via these namings. And then, of course, that's the most important thing, these wavy arrows, which are what we call views, which are essentially theory morphisms that come with proof obligations, namely that every axiom, when translated, becomes a theorem in the target theory. And if you do that, you can move theorems around, like any monoid theorem will be true in natural numbers with plus. And so theory graphs, and that's, I think, the most important thing, theory graphs are a giant copy machine. You get much more out of it than you put into it. The picture I always think about is if you have the library, then you have kind of a represented core which induces a space of theorems that is much, much, much bigger. And if you have cycles in the views, you might even have it infinitely big. And the big innovation of the MMT system is that every induced object has a unique name, which is a URI, a global name, which allows you to make many, many, many things incremental. Which allows you to do garbage collection and all of those kind of things. And so that's a big invariant we want to keep. And then the invariant is essentially, if you know the name and if you know the represented library, you can reconstruct the object. It's wonderful for search, by the way. If you search for associativity of plus, which in this theory graph is not here, why not? Because it comes into, say, the natural numbers of plus via this here. It's a copied thing, it's a copied axiom turned into a theorem along the way. So if you wanted to search for that, what do? You take the graph, copy everything, dump it into something like MathWeb Search, which has almost infinite space, and then search for it, and then if you have the URI that you get back, then you can use the URI for explaining why this is actually a hit. And you can build this. Views occur in nature. Think about, you all know how to convert temperatures into Kelvin and Fahrenheit and all of those kinds of things. Those are views of the various theories of temperature. Now, all of that is formal. And if you think about the copy machine, here we can only copy the theorems. Wouldn't it be nice, if we're doing things like education or so, if we could copy other things? The thing I would love to have copied most are quiz questions for our Alia system. We need these quiz questions to diagnose competency, which means that for my AI course alone, I need something like 5,000 quiz questions as diagnostic elements. Who's going to write them? Well, my students aren't going to, and they have to be well designed, and they have kind of to have they're like unit tests, right? Unit tests are a lot of work, we all know that, and they have to have some coverage conditions and so on. So they're really high ticket items. Wouldn't it be nice if I could have a quiz question here and kind of along every path in here have the right way and have the path tell me of which questions to move where. There's a lot of very important information here. The views, if looked around in the other direction, are actually examples. They're also, if they go into ZFC or so, they're models. And all of those kind of things we can put into these graphs But we have, if we put other things like examples into them, if we put problems in them, explanations maybe, feedback to problems, all of those kind of things can be copied over. And we're doing that. Marcel is doing his PhD thesis on those kind of things. And so that's really what I'm after with this. And so we need to have, I'm going to finally say it, libraries of flexiformal mathematics. And the question is, how do we do that? Because if you look at what is a theorem or a definition or an example or those kind of things in Lean, it kind of looks different. Right? It has another composition and it looks different. And yes, we try to make it look somewhat similar, but it's, for the uninitiated, unwashed masses, it's not obviously the same. So I would like to propose something that's been done in the open math, MathML arena, and the idea there is that we kind of represent our objects in two ways. One as a layout tree, it's called presentation MathML, and as an operator tree, and it's called content MathML, and you basically cross-reference the corresponding parts. It's called parallel markup, and while this is probably not the right way of actually writing it down, this, for the machine, is exactly what you want. If you click on that, you can select that subtree. That's really the things you want to do, and many of our systems actually, somewhere in their math DOM, to do something very much like that. There's an XML, I don't want to. This was for formulae. We can also, I claim, do it for the higher level things, like statements of theorems, like conjectures, like definitions, and so on. And I've brought you a definition of the exponential function. In formal things, in this case, pseudo-MathML, pseudo-MMT, where it's basically a constant definition, a constant declaration of the exponential, which has a type and a definiance that tells us what the semantics is. Now, that's not something you see in a math book, and if you're not sufficiently brainwashed enough, which many of you are, you will actually be able to distinguish it with something from a math book, which might go like this. Right? But there are things that you can see that are the same. The E here is exactly that constant. There is typically something like a pseudo type, which is not really a type because math doesn't really have a type system yet, but something like a soft type system. And then we have the solution of f prime, blah, 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 blah. And so we can co-reference those, and that's really what we need for our systems if we want to do it, and have that in all detail through all of the text. And if we have that, we can actually do things like transport quiz questions. How do you implement that? Well, we've done our experiment with something called STEX, which basically adds into something that does text well and formulae, LaTeX, annotations of formality. So this definition 0815 comes from a \begin definition with an identifier and possibly a couple of other things in junk. This here basically comes from semantic annotations, which in the PDF don't show up, but allow us to have those things as well in one source. Add both of the things, and then we build systems that put these things together. I'm not going to go through the proof. The thing I would like to make you aware of, that flexiformality has a big design space. So if you have two theories, one is along vector spaces, the other one is metric spaces, you all know this, then a norm induces a metric, right? Absolute value of the difference. Then the views, I've put as squiggly arrows, in the formal setting would have to have a proof that basically takes all the condition that I've put up here and kind of verify that after translation satisfy all of the condition that are down here. Right? And we can all do that, 5 minutes, not a problem. Right? But a system can or cannot do it. But a view which has an object in our flexiformal ontology, which I would like to keep intact, is something that has these, is an object. Now you can make a view by just saying view column or begin view end view. And there is a view, and then you say something like, Michael believes this very strongly, right? Michael believes this very strongly is in essence a proof, right? Of course, with no machine actionable content. Except maybe for the people who know who Michael is, right? They can trust that or not. And that's one way of doing it. That's flexiformal. Or you could say, but there's a mapping here involved in this. And if you do that, you still don't know whether this is truth preserving because there's no proofs in here. The obligations aren't even stated here. But you have a partial mapping, and that is exactly the level we need for actually transporting quiz questions. Because verification in education, let's face it, is not a problem. The things I put in my classes are true because I'm a professor and you're not, right, dear students? Right? So verification is not a problem. They can do it informally, but for the system, it's not. Right? It's because I say so. So maybe this is a better level on this functionality graph. But you can also do even more by saying, there's 3 conditions we need to do something about. More information, more formality. But I'm not telling you what the proofs of the side conditions are. Some of them I might just leave open in an exercise or a problem. But there's at least something you can start by proving these 3 things. We have all these levels in flexiformality, and we can keep, that's for me the important thing, the theory graph intact. And of course, you can, just to make all of the formalizers in here happy, you can also give full proofs, and it's still flexiformal. Right. So the way I would like to show you the theory graph, it's essentially for a formal system. Some parts are just blacked out, right? I think somebody came here with a big pen, and that is flexiformal. We're not telling you everything. You could make some of these gray and show some of the contents, and maybe humans can do something with that, but that's what flexiformality is. Right. Andrea is giving me signs that I should shut up. I'm going to shut up. In this case, you're not my primary point of reference, as long as Valeria allows it. Oh, go on.
We started 5 minutes late, so I think now we're getting over.
I want to show you a little bit of STEX. If you really want to know about it, ask Dennis. He's basically come to my office at some point and says, after his PhD, and says, I'm going to dedicate my life to STEX. And I was very happy, and then he said, but you're doing it all wrong. And I was even happier because, of course, and we can harness all of that brain power, and that's kind of happening. He's told himself we're doing it all wrong, and then so we've had a lot of 5 years of a lot of fun developing this further. Right? This is what you see in the PDF. It's overhead. It's overhead writing this. But you're also adding value. This is flexiformality at its best. And if you look at it, we are mixing informal and formal in here. We are using fully formal formulae via these SIMDEFs, semantic macros. But we're also using formal annotations that says, well, here we're starting a definition, here it ends, afterwards is something else. This is the definiendum Semi-group, and it's defined that I haven't done, but you can do it in STEX. But for me, when I'm teaching, it's too much overhead, so I don't do it. Dennis does it, and he can do more with his stuff. There could be type annotations. We can export the whole thing into MMT, which does type checking then, and basically does that. No, you can't do that. Those kind of things. This is flexiformality, how we experiment with it. We've been doing quite a lot of that. We have something like maybe just one numbers. We have 16,000 STEX files over many Git repositories. We have 15 courses with thousands of problems and slides and so on. Yes?
Do you have the training data? Do you have the original unannotated, unsemantic documents?
No, but we can. There's a little tool called, and it's decades old. It's called Detechify, that gives you exactly the right thing.
But that's slightly different, right? It's like that's like producing synthetic data, like, or do you think that would be equivalent to?
I actually write my slides, flexiformalize them in LaTeX. And then later go to find all the, and then I ask Dennis's linter, and it tells me, but I don't really, I don't let the annotations dictate what we're seeing, except for, say, the colors.
Okay, well then, very easy question, like ask somebody like them to train a language model on.
Yeah, I have a variant of this. Ask somebody like Frederick or Dennis to train a language model on this. And
whomever is doing the work.
Dennis does it on archive, and we do it on other stuff. Yes, we've done that. Yes, Dennis.
On that note, like if you're looking for the plain LaTeX equivalents of our STEX stuff, that probably doesn't exist anymore. But in the 6 months I spent with Cesarik in Innsbruck in 2020, I basically wrote something that tries to do exactly that. So just take the STEX stuff, expand all of the stuff, convert it to plain LaTeX, precisely because I wanted to have a parallel call. That could be brushed up again, and it probably will at some point once it like gets further up on my to-do stack.
Yeah, sounds good.
Yeah, so my conclusion slides, I've talked a lot about the missing question, and I hope you talk a lot about it too. I've tried to convince you of flexiformalization, which is really take informal stuff, because that's the difficult thing, and mix in enough formal information, and that could just be a begin section or something like this. Such that you can get, and that's maybe the most important thing about the answers, is if the further down we got in the answers, the more it was about one bit of information saying, yes, we have a proof, but about the artifacts that are made in between. And the really nice thing about the education application, which includes scientific publishing, because we are teaching to each other in different roles all the time, is that you have loads and loads and loads of little artifacts that you're combining in new ways. All of you, when you give a talk, take old slides and you reuse them in a slightly different way and try to organize that. All of that is flexiformal math. And so we get into the game of playing with artifacts. We're still learning that. One of the things I'm learning here together with Anna is that if the artifacts aren't annotated strings, but we parse the rest of the language with GF, then we can do all the replacements we have to do in moving quiz problems from one theory to another one, from propositional logic to first order logic to modal logic, where the same problems become different guises. If we do that abstract syntax trees to abstract syntax trees semantics, we get all the inflections right. How nice. Right? So there's still a lot to be done, and I think we should be, as a community, doing more of it. We're building this relatively big corpus, not quite as big as MathLib, and not quite as advanced as MathLib. I think of it as MathLib minus. Basically, undergraduate math and computer science, that's what we're building right now. Then we build semantic services on top of that for teaching, for scientific communication. All of our papers and my slides are in STEX, so you can actually get additional services, things you usually only get when you actually corner me and drag me in front of a blackboard. That should be some things the active documents should do for you. And we know how to do this. We need flexiformalization.
Thank you.